So we're going to talk today about how to display and then describe categorical data. So your book, Being Funny, said there are three rules of data analysis, and they are make a picture, make a picture, make a picture. Right? It's like, have you guys ever heard the saying that the three most important things in real estate are location, location, location? It's the same kind of deal. They're like, it making a picture is super helpful because when you just look at raw numbers, it can be really overwhelming to try and get your head wrapped around it. So, why do you make a picture? One is to help you think clearly about the patterns and relationships. You can kind of see relative sizes, all those kinds of things. Make a picture to show the important features. A picture may show things you didn't expect to see, like an extraordinarily or possibly wrong data value in a set, or some unexpected pattern where you're like, oh, I didn't think that was going to happen. Or, it's like something is like, why is this zero here in the middle of my data set? What's going on? And then also to communicate, to tell others about the data. Okay, sometimes you can look at a picture and it immediately makes everything make sense. A non-statistical example of that for me personally was, you guys have done line of best fit, right? You've got a set of data and all that kind of stuff. So it's based on a thing called least squares, okay? And what you actually do, and we'll talk a little bit more about this later, but I wanted to just highlight it. Basically what happens is this. You've got some sort of deal and you've got all these points, D, and you have a line of best fit that does like this. And what you do is you actually drop in this distance and create a square, and this distance and create a square. And what you're looking for is the line where the sum of the areas of those squares is the least. I didn't understand why they called it a least squares regression until I saw a picture of that, and I was like, oh, you just want to make the squares as small as possible. Got it. I mean, I went from not really understanding it at all to completely understanding it in about half a second, because the diagram made sense. And since I'm a geometry guy, pictures help me a ton. All right, so one of the first things we have to know is the area principle. Spelling is really hard. Says that the area occupied by a part of the graph should correspond to the magnitude of the area it represents. And you're like, what the heck are you talking about? So you will occasionally see things where they will have cut off part of this and they'll say, this is 50 and this is 500. Right? Those areas are, it's not proportional. The area of that second one should be 10 times bigger than the area of the first one. It's one of the ways that you can lie with statistics. Okay? Or you can show a picture that leads them astray. All right? So, we're still working with categorical data, or we will be working with categorical data in this chapter. So one of the first things you do is to count how many in each category there are. When we put this on a table that records and totals the category names, we have a frequency table. And the example that I used these out of your book. This is from, have y'all read the part about the Titanic yet? Okay. So this is how many people were in first class, how many people were in second class, how many people were in third class, and how many crew members there were. Now, when you just look at those, it's okay. I mean, it is the raw numbers, and it does give you context. But getting the relative sizes of those, unless you're really, really, good with numbers, it's a little harder. So a lot of times we'll want to know the fractions or the proportion of the data in each category. Usually we use percentages. You don't have to, but most of the time we use percentages. And this is called a relative frequency table. And that's in this second table here, where we can look at the percentages. I would argue for something like this, if you're just trying to get the point across about how many there were of each, I wouldn't have done any decimal places. I would have rounded it to the nearest percent, because then it's faster and easier to look at. Now, do you lose a little bit of accuracy when you do that? Yeah. In terms of, because you really want people to be able to look at something and boom, they've got an idea of what's going on. So both types of these tables show how the cases are distributed across the categories. In this way, they describe the distribution. We're going to be greatly concerned with distribution of a categorical variable, because they name the possible categories and they tell how frequently they occur. Okay, so how is this divided up? So one of the things that we will use is a bar chart. A bar chart displays the distribution of a categorical variable. Bar charts always are for categorical variables. Later on, when we get to numerical variables and you're using bars, it's no longer called a bar chart, it's called a histogram. Showing the counts for each category next to each other for easy comparison. Bar chart should have small spaces between the bars to indicate that these are freestanding bars and can be arranged in any order that you want them to. Because for categorical data, you don't have to do it in any particular order. Now, just personal preference, I like to do it so that I have the biggest on one end and the smallest on the other end, and they're in order. But it's not super important that you do that. If we replace the counts in a bar chart, and I should have added with percentages, we get a relative frequency bar chart. And you can see how this kind of gets silly after a while with the names. So the data that is in these two tables up here has been recreated down here. This first one is a bar chart for just the frequency. And the second one is a relative frequency bar chart. Now, what's one of the things you immediately notice about these two bar charts? I'm sorry?
They're representing the same data?
Yep, they're representing the same data, just about the picture though.
The bars are the exact same size.
Yeah, they're the same size, which makes sense, whether it's counts or percentages.
So it really doesn't matter.
Yeah, it really doesn't matter a whole lot. And actually, we'll find that when we're doing calculations with it, it doesn't matter either. okay? But in terms of a table, the percentage is a lot easier to look at. But once you're looking at a picture, it doesn't really matter a whole lot, because this picture allows me to kind of get the idea of the relative sizes quickly. Now, on this one, I talked about, going greatest to least or least to greatest. Why is that probably not a good idea on this one?
Like first, second, or like second, third.
Right. There is an order that kind of makes sense on this. First class, second class, third class ought to be in order. If you wanted to put crew first instead of crew last, that's fine. But, or, I guess if you were, feeling particularly egalitarian, you could start with crew first, third class, second class, first class. Right? All right, let's move on. Page 2. So if we take a circle and slice it up into pieces whose sizes are proportional to the fraction of the whole in each category, we get a pie chart. And just a quick note on pie charts. You've seen pie charts a ton. I'm not going to spend a lot of time on them. Two things. One, it's best when the relative frequencies are close to a half, a fourth, an eighth. I would add a third to that. Your book didn't say that, but things where it's, fractions that you can kind of see. And they say or, but you don't want to have a ton of categories, right? If you've got 23 categories, a pie chart is not a good way to go. It's so broken up, it doesn't help you get the complete picture. And for most of the things we do, we don't do that many categories anyway. So it's usually not an issue. All right, so one of the things you have to do before you draw something is you want to think about it. The categorical data condition says for a bar chart or a pie chart, the data must be in counts of individuals in categories. Now, notice that's the original data. If you change it to percentages, that's fine. But your original data needs to be counts. All right, so far, we've only looked at what's called univariate data, where there's only one variable. And honestly, univariate data is fine for giving some context, but there's not a lot you can do with it. When you look back at this, you're like, okay, there were more crew than anything else. And interesting, more first class passengers than second class passengers. Huh, and you're pretty much done. Right? There's not a whole lot there. But when you get bivariate data, it gets a lot more interesting. So in our class, and again, this is from the survey we looked at the other day, a question that you might want to ask is, are girls in our class more likely to be politically liberal than the guys in the class? By the way, if I remember correctly, that year it turned out absolutely it was that way. It wasn't even close. Because we did it with AP students, you don't see this, but if you did that on age, for example, younger people are way more likely to be liberal than older people are. And it has always been that way. I have a good friend who used to joke, and don't report me to anyone, but the joke was that if you're not liberal when you're young, you don't have a heart. And if you're not conservative when you get older, you don't have a brain. And I was like, okay. I mean, and it's way overstating it, but there's some truth in that. All right. So, are boys more likely to have larger shoe sizes? These are frequently more interesting questions. So, questions that show how the variables are distributed along two variables contingent on the value of the other variable are called, key word here is contingent, contingency tables. Each cell gives us a count for a combination of values of two variables. So, I don't know why this says at right. The table at left gives the politics and the sex of a particular statistics class composed of college freshmen. The bottom line is the frequency distribution of politics. So it shows you the frequency of the three different political. They did liberal, moderate, and conservative. The rightmost column is the frequency distribution of sex. There were 77 females and 115 males. When it's presented like this in the margins of a contingency table, this is called marginal distribution. So the contingency table itself is actually just this part. And then when you add on the margins, you can get the marginal distribution. So for example, in this table, the marginal distribution of politics is 85 out of the total 192 were liberal. So you could do a relative frequency marginal distribution, and this would be 44%. And then 42%, 14%. And there's all kinds of questions that we can answer when we get a table like this. So, what percentage of the class are women with liberal political views? You have to pay attention to the of the class, of the something, right? So that's telling you your whole group. So how many people were in the class? 192. That's going to be your denominator. And in this class, how many of them are women with liberal political views? 35. And that comes out to be 18.2%. Now, here's where it gets interesting. These next two questions, it's really easy to think that those should be the same. What percentage of the liberals are women and what percentage of the women are liberals? Okay? It's the of the whatever that's really important. What percent of the liberals?
So of whatever is like the denominator?
Yeah. Of the liberals. There are 85 liberals. That's my denominator. And I'm only looking at the liberals. So how many females are liberal? 35. So it's 35 out of 85, which is 41.1%. What percentage of the women are liberals? So now I'm looking this direction.
35 out of 77.
Yeah, 35 out of 77. Which is 45.5%. So if we take the table and we divide each cell by the table total, we can get a percent of table values. And it turns out, if I go back up to here, where let's say I did what percentage of the women are liberals. All right, so of the women, it was 40% total, right? And there were 18% that were liberal. That also comes out to be 45.5%. Because we have taken every one of those numbers and divided it by 192. So those 192s would actually cancel if you left it in there. So sometimes people prefer these tables rather than the raw numbers, especially if the numbers are really large. All right, so we can see in this table that 19% of the students in the class are moderate females, 23% of the students in the class are moderate males. Does it mean that males are more likely to be moderate than females? This is where you can get into trouble on this. You're like, oh, 23% of the guys are moderate, 19% of the girls are moderate. Does that mean that males are more likely to be moderate than girls?
No, because there are also a lot more males.
Yeah, there's also a lot more males.
So really, it's probably more women.
So we're actually going to look at that tomorrow. Got to leave you hanging a little bit.
Wait, I have a quick question.
Yes.
So you said 18% over 40%. When I put in my calculator, I get like 0.45. How do you get like the other?
Got to move the decimal 2 places to change it to a percent.
Oh, I did it times by 100 and I still get 45%. Like, how do you get that last 0.5? Like, I'll show you later.
So if you do 18 over 40, probably because with the, how I said you lose some accuracy?
Uh-huh.
It's probably not exactly 18%.
Ah, okay.
So you lose some accuracy when you do it this way with the 18% over 40% because we've probably rounded it to the nearest percent.
Okay, yes.
So it's going to it's going to be close.
Yeah.
And one of the interesting things in statistics, frequently we're more concerned about getting close than we are concerned about getting the exact answer, which drives some of the math students a little bit nutty because they're like, what do you mean? I can just round it wherever I want. Yeah, round it wherever it feels good to you. And you can see people start to melt down. No, I must have the exact answer. Good question.